All right, so our next topic is higher order derivatives. This is a very basic topic. Most students have very little difficulty with this. Higher order derivatives is one of the most standard and very ordinary topics in the section here. In fact, in all of Calc 1, in fact, the textbook presents this in just half of a page. There's not a lot here. The notion of the higher order derivatives is this. Here it is. I have two little functions just laying up here waiting for their derivatives to be found. Maybe I should call this one g of x so I don't have the same symbol meaning two different things. Here's function f, here's function g. We can find these derivatives. This is just the power rule just waiting to happen here. So we can find in each of these cases, we can find the derivatives. So here's f prime of x. And the derivative here, that's 8 x to the third. And then we got, what is that? Negative 6 times 3 is 18, x to the second, and the derivative of 8x is 8, and that's all there is to it. And then you can say, okay, well, now I'm feeling so good about myself, I'm now going to go compute the derivative of that little polynomial, and then just one little pause makes you realize, wait a minute, this is the answer I just got. I'm going to be finding the derivative of the derivative. Now, that can be done, no problem here. This is g prime of x is 24x to the second and 36 minus 36x. That would be wonderful. We can certainly find the derivative of that function. But you see what we've actually done? Finding the derivative of this function is the same as finding the derivative of this function, because the symbol g of x and the symbol f prime of x are the same. They represent the same function. So if we wanted to, I could rename this f prime of x, and then this is the derivative of f prime. And you see what I've generated? F double prime. This is the second derivative. The second derivative. It is simply the derivative of the derivative. There's a reason why this needs to be done. In the next chapter, we'll talk about there is a representation. What does that correspond to? There is an interpretation. It has all these wonderful uses. For now, just be able to find it. Now, if it's a polynomial, this is easy money. The polynomial if these are polynomials, the derivative of f is f prime, and then you can find the second derivative. In fact, we've already done it. This is 24x to the second minus, what is this, 36x to the first. Derivative of the constant vanishes. And, as Dr. Guffey used to say, you had so much fun, do it again. If you can take the derivative of the derivative, getting the second derivative, in fact, we call this the first derivative. This is the second derivative. Well, it's not very hard to figure out what's going to come next, and it's not very hard to figure out what the symbol's going to be. The symbol's going to be this third derivative, which is the derivative of the second derivative. Just keep doing it until you're blue in the mouth. In principle, this could never end. You could do this as many times as you felt led by the Spirit to do it. The derivative here is 48x. Now, some students say this process does end. It does not. The fourth derivative, now usually we start using little Roman numerals here. Usually the superscript is little Roman numerals. So this is the fourth derivative. Derivative of 48x is 48. And then we can find the fifth derivative, and the derivative of a constant is 0. And students say, well, this is where it ends. No. We can find the sixth derivative because the derivative of any constant, no matter what, is 0. The seventh derivative is 0. The eighth derivative is 0. The phrase is higher order. We say all higher order derivatives are 0 in this case. So it's not correct to say the derivatives stop. It is correct to say in this scenario, because this is a polynomial, and that's a key element, because this is a polynomial, the derivatives eventually zero out. But they are all present. The derivative is zero. It does have an interpretation. Now, this does not always occur. In fact, unless it's a polynomial, typically it won't occur. If all you're working with is polynomials, then this is very straightforward. Just find the derivatives of the derivative using the power rule over and over and over again. It does not always go to zero, and we can see that fairly easily. It's not very hard to show this does not go to zero, because if you choose any function which is not a polynomial, almost certainly this is not going to happen. And it doesn't have to be very complicated. Look at f of x is equal to tangent of x. Let's do secant of x. All right? What's the derivative of secant? Well, we know the derivative of secant because we know the derivatives of all our trig functions. The derivative of secant is secant tangent. See, sometimes when you find derivatives of functions, they don't simplify like polynomials. Sometimes, this is Dr. Guffey used to call this, they complexify. And so now if I want to find the second derivative here, I'm going to have to steal some space. Because the second derivative requires the product rule. It's going to be first times derivative of the second plus the second times the derivative of the first. And so these get more and more complex as you go. So this is going to be first times the derivative of the second plus the second times the derivative of the first. And this is going to get complicated. So this is first, copy, paste. So now you're showing off your skill using the product rule. First times derivative of the second. The derivative of tangent is secant squared. Those need to be automatic. The derivatives of the trig functions need to be automatic. First times derivative of the second plus the second times the derivative of the first. The derivative of secant is secant tangent again. And if all you're asked to do is find the second derivative, then you do not need to simplify. If you are asked to simplify for some reason, if you're required to simplify for some reason, then yes, do it. If you are not required to simplify, then leave it alone. In fact, there are going to be times on the exams I'm going to say explicitly, do not simplify. I want you to leave it in this unsimplified form for reasons that become clear later on. So for us, for now, there's the second derivative. So the point is, it doesn't always go to zero. And we can see, if you took the derivative of this thing, it's going to continue to get larger and larger and larger. All right? Other scenarios where this occurs. Other examples of second derivative, and it can be a very simple little function. F of x is, suppose I take x to the negative 4. What's the derivative of that? That's negative 4x to the how much? Well, it's going to be negative 4 minus 1 is negative 5, not negative 3, negative 5. And then we can take the second derivative, which is positive 20, x now to the negative 6. And see, this is never going to go to zero because these continue to get larger and larger negative. Third derivative, if you wanted for some reason, that's negative 120 times x to the holy cow, negative 7. Oh my goodness, if for some reason I can't imagine why you wanted the fourth derivative, this would be positive 720 x to the negative 8. And I'm getting tired of that. But you can see these don't zero out. Now, typically for our work, now when you get to Calc 2, there are some places where you get a little more sophisticated. But for our work for now, the only thing I'm going to be asking of you, typically, is the first and the second derivative. I might ask you to do a third derivative just to see if you're on your toes. But typically, the only thing we'll be working with is the first and the second derivative. All right? Most of what you do, for example, in physics deals only with the first and the second derivative. Some of you know already we have velocity and we have acceleration, and the third derivative is sometimes called the jerk. It's a concept in physics. Most of our work, we will limit ourselves to the first and second derivative. Another thing that can occur is something like this. This is kind of a nice little cycle to work through. F is sine of x. F prime of x, derivative of sine, is cosine. Second derivative, the derivative of cosine is negative sine of x. Third derivative, the derivative of negative sine. Now this is a constant multiplier. This is -1 times. Constant multipliers multiply along, and the derivative of sine is cosine. And then I'm running down the spacer. I'm going to just rather than continue, I'm going to bring it up here to save myself some space. So we could do the fourth derivative. Better do a 4 like a Roman numeral here. Now, how does this work? It's -1 times cosine of x. So the constant multiplier multiplies along. The derivative of cosine is another negative. Right? So it's -1 times negative sine. That's positive sine. And what we can see is we're back where we started from. And so this cycle continues. It just continues to cycle through, and that has some applications in higher mathematics as well. Anytime you generate a pattern in mathematics, it's like that's golden. You can use that for an application somewhere. But again, you can take derivatives till you're blue in the mouth. It's never going to go to zero. So that's the notion for higher order derivatives. For now, just be able to find them, be able to work through them, and it should be pretty straightforward. What I'll do next, I want to do a separate little video with some more challenging second derivatives. I might actually have to wait until we're through with the chain rule, and then when we come back and you look at the second derivatives, that'll help us on some of those computations. So next up is we're going to do the chain rule. Once we have the chain rule, then we can actually consider the second derivative of a few more complicated functions.